So today's speaker is Marie-Hélène Bull, WestGrid trainer. And today she's going to talk about Julia and using Julia in the HPC environment.
Good morning, everyone. So indeed, I will talk about Julia in the context of high-performance research computing. So just to give a tiny bit of Julia background. So it's a language that's extremely recent. It started in 2009. Jeff Besançon, Stefan Karpinski, Viral Sa, and Alan Edelman launched that project in 2012 as an open source free software. The version 1.0 was only released in 2018. So it's still evolving very fast. It's a very capable language, but more and more features keep being added, and it hasn't reached its full potential yet. So why did these people decide to create a new language while there are so many languages out there? The main reason is that they were frustrated to have to use two languages constantly. They were doing a lot of their work in, for instance, Python and C++. So why is that? There are two main categories of computer languages, compiled languages and interpreted languages. Compiled languages are extremely fast. C, C++, for instance, are compiled languages, but they're quite hard to learn, and they require a two-step process. You write the source code of in the language, then you run it through a compiler to get machine code that is going to be readable by the machine and extremely fast. And then it is this machine code that you use to get from your input, your data, to your output, what you want to get at the end of the line. It's extremely fast, but it doesn't allow any dynamic interaction with the language. And the other category of languages, interpreted languages, such as R, Python, for instance, are much more convenient because, first, they're easier to learn, and an interpreter deals live, so to speak, with your source code and the data. So you can interact with the language, and that's what makes, for instance, R or Python so dynamic, and that's what brings the convenience of the Python shell or REPLs in other languages. So the authors of Julia were using Python as an interpreted language to do a lot of their scientific development and thinking, but then because Python is pretty slow, they had to use C++ to speed up their code where necessary. And so there was this dual thing, and they wanted to have a language that would be at the same time interactive and fast enough. Julia is one of the few languages that uses just-in-time compilation. So just-in-time compilation allows a workflow that's similar to the interpreted language workflow, but some compilation does happen just before the code is actually run. So you have at runtime compilation. So the first time you run a bit of code in Julia, it is a little slower because you have the compilation that takes place, and on top of it, you have the interpretation. But then once the code has been compiled, a lot gets put in memory, a lot gets buffered in, and there are also a lot of micro adjustments and little tweaks so that the compiler can decide whether the overhead of compiling is worth it compared to the speedup that's going to be achieved. And Julia is not as fast as C or C++, as some claim, but it's way faster than interpreted languages, and you have access to a Julia REPL, which is as interactive as R or Python. So you kind of have the best of both worlds. It's a bit of a trade-off, but it works pretty well. In addition to just-in-time, something that makes Julia much faster is multiple dispatch. And that multiple dispatch is built in. It's not function overloading. It's really part of the language. And so multiple dispatch is when functions can apply different methods at runtime depending on the type of the operands. So the sum function, the plus function, for instance, has in Julia 160 different methods. So if you run 2.0 plus 2.0, you're going to use the float method of the sum. If you run 2 plus 2, you're going to use the integer method of the sum. And that allows to apply the method that is really the best suited to the data type that you are using. It allows also a lot of optimization, a lot of checks. But in addition to that, you have an option to declare the type. If, when you define functions, you declare the type of the various operands, that's going to speed up your code immensely. If you don't do so, things will still work. Julia is very flexible in this respect, so you can write code very easily and fast, which is convenient. But without type declaration, you lose a lot of the speed, and you may end up in the kind of speed that you would achieve, for instance, with Python. Julia is not nearly as used as Python, but it has a pretty large user base, and it is a very dynamic community. So there are lots of documentations and resources out there, and I will post these slides online, and from these slides you can follow links to a lot of resources. There is, of course, the official Julia website and the official Julia manual, but there are also online training material. They have a YouTube channel, there is a wiki book, there is a blog aggregator just for Julia. And if you need help, they have a discourse forum. Of course, you can ask questions on Stack Overflow. They have a Slack team. There is a hashtag on Twitter. There is a subreddit channel. They have many GitHub channels, one for the language and one for packages. You can even contact them through IRC. So there's really a lot of resources out there. And if you want to run, since Julia allows dynamic feedback from the code, as you would get in an interpreted language, as you develop your script, it might be nicer to be able to send your code directly from your growing script to the Julia REPL rather than have to do some awkward copy-paste. So there are some pretty nice interfaces that allow to work smoothly in Julia. There are 3 different options in Emacs. What I will be using in this webinar is the first one, Julia Emacs with the Julia REPL, so 2 Emacs packages. But there are other Emacs options. Julia also has a dedicated IDE called Juno that was built on top of Atom. And the Jupyter notebooks have a Julia kernel. So you can also use the project Jupyter with Julia.
Mary, there's a comment in the chat about type annotations. So from Mason, maybe you want to comment on this.
Sure, let me read it. Because I was ignoring comments now because there were lots of them, but thanks, Alex.
Was saying was just that you mentioned that you need type annotations to get code specialization, which is not true in Julia. It'll generate native code for any input type.
I thought that by specifying the type when you define a functions, you could optimize your code. Is that not your understanding of
No, that is not true.
Okay. So what is the benefit of...
Sorry, I don't mean to interrupt.
No, you're raising an interesting point. So I can't spend too much time on that, but let's please go ahead.
So if you type f of x equals x plus 1 in the REPL, and then ask for the native code generated by f of 1, you'll see that it is specialized code for integers, and this will happen for any type, and the type inference will do that for all enclosed functions inside a function.
Yeah, that's right. But then if you rerun it and for x, instead of running 2, for instance, if you run 2.0, it will have to be recompiled because the first time it was compiled for an integer, and now you're using it for a float, and it will get compiled.
That's independent of the type annotations, though.
Yes,
That'll
but
happen
if in
with
your
or without.
yes, but if in your function you had defined that x was a float, then when you ran f of 2, it will still, I think, consider that 2 is in fact the float 2.0, but I might be wrong on that. And so I think you might.
No, it won't automatically convert like that.
Okay, all right. Okay, so I'll have to go back to the advantage of defining types. I guess it could lead to errors, so it might be an error checking, but I will have to look into this optimization aspect, because apparently what I had understood is not necessarily correct. So I'll, thank you, I'll check that out. So let's have a look at the Julia REPL. So REPL stands for read, execute, print, loop. So it's a form of shell, dynamic shell. In the REPL, you can use the standard key bindings that you could use on the Linux shell, for instance. You have a little list here, but they're very standard key bindings. In addition to those key bindings, there is let me launch a little Julia shell. A nice little things specific to the Julia REPL. You can get into various modes. If you type the semicolon, you get into shell mode, and you can type here some bash commands. For instance, if you want to print your working directory, you can type a Linux utility like pwd, and it works. Another mode is the help mode that you enter by typing the question mark. And if you type the name of a function, you will get help on that specific function. And to get out of any of these modes, you can press the backspace, and that leads you back into Julia. Another mode is the package mode. Julia comes with its own package manager, and you can install and update, etc., all of your packages very easily through this package mode. And what you see between brackets is the environment in which you currently are, because Julia has a system that's called project, but it's a virtual environment where you can define sets of packages at specific versions in a fashion very similar to Python. But where do you find packages? So Julia comes with a lot of standard packages. When you install Julia, you install a number of packages already. But there are many packages that are developed out there, and all the registered packages are on GitHub. And there is a search engine that let me get out of this. Allows you to look for packages very easily. Thanks to the star GitHub system, you can very quickly see whether a package is used and appreciated a lot or not, which can be convenient. There is a link to the GitHub repo so that you can see whether the package is actively maintained or whether it's kind of fallen a little out of use. You can easily search packages for various themes, for instance, if you want to do some plotting or some machine learning. So that's pretty convenient. Of course, you can build your own packages, or you can find unregistered packages elsewhere, but the registered packages are in an easy central place on GitHub. So as I mentioned, you can do all of your package maintaining, installation, etc., very easily in the package mode, simply through those little functions, add, rm, st. So for instance, if I go, here I am in Emacs. I'm using the two Emacs packages that I mentioned. So on the left is a script I have, and on the right is the Julia REPL. So if I enter the package mode, and if I press ST for status, that gives me a list of the packages that I have installed on my machine. So it's a very easy and convenient way. Before you can use the functions that are in a package, whether it's a package that you have installed yourself or whether that's one of the standard packages, you have to load it into a session. And that's something you have to do, of course, at each session. And the function to do that is using. So if you type using plots, for instance, plots is a package, then you can use the functions that are into plots. Now, let's start to play in Julia a little bit. So as Julia is a language that is heavily typed. The implementation of type is very strong and very powerful. So there are a lot of types, and they follow a big hierarchical structure. At the bottom of that tree, you have the real types, and above you have abstract types. For instance, if you want to add an integer and a float, you can do that because both of them belong to they have an abstract type in common. They're both numbers, and so that works. But it would be a lot faster to run 2.0 plus 2.0 than it would be to run 2 plus 2.0, because you would be using the true types and the float method of the sum function instead of using an abstract type and one of the methods of the sum function that is designed to handle those asymmetric types, and that's much less optimal. So being careful of types is important. 2 and 2.0 are two very different things. So let's have a look at a few types, extremely simply. So 2 is an integer. The function to look at the type of any element is type of. 2.0 is a float. Hello, unsurprisingly, is a string. True is a Boolean. So as I said, there are very many types, but this is just to give you a very small idea of the function type of. Excuse me. Sorry. Now, let's build an extremely small, extremely simple array that, let's create that variable a, which is a 2 by 2 array. So it's as you can see, it's a 2-dimensional array made of integers. If you want to index that array, as in many languages, you use square brackets. So a square bracket 1, 1 would index the first line, first column, so that's the element 1. If you wanted to index the first line, but in some languages, such as R, you would leave a blank space for the second value, but in Julia, you need a column. What about for loops? Well, also very standard, nothing very special there. And to close functions and while loops, for loops, etc., is the Julia keyword. So very simple function here. For loop, for I in 1 to 10, print ln. Print ln is the function to print an element and have an end of line at the end. So for I in 1 to 10, print ln I, whoop, we have our 1 to 10. If now you do it, if you loop over I and j, that works in a similar, easy fashion. Now let's have a look at just a little if-else code. So A is going to be will have the value 2, B the value 2.0. Now, if I run this code here, if A equals to B, print it's true, else print it's false. If I run this, I get it's true. So A is equal to B. Now, since Julia is a heavily typed language, something that is quite interesting is that you also have a triple equal sign symbol. And look at what's going on here. I'm running the exact same if-else code, with the only difference being that this time I am using the triple equal, and now this time I get it's false. So A is not equal to B because the triple equal checks not only for the value but also for the type. There is also a much terser format. This line is the exact same one as the preceding code. You can write your the conditions that needs to be checked at the start, question mark, and then what to do if it's true, colon, what to do if it's false. So this is a terser version of the exact same code. Now, what about writing functions? It's very similar. It adds this end to close the function. Unlike in C or Python, return is optional if you want to return the last element of a function. You can use return if you want, for clarity or out of habit, no problem there. And you will have to use return if you want to return other things beside the last element of the function. But if you only have one element, or if it's at the end, it's facultative. So here I'm creating a function that I'm calling add2. So as you can see here, we have created a generic function with one method. That means that add2 for now has only that one method. We could add several methods to this easily. It's a function that takes one argument, and it adds 2 to this argument. So if I run my new function on the value 3, well, add2 using 3 as an argument gives us 5. And as you can see, the result 5 was returned even though I didn't have return in my function. There is also a terse format for add2 below. This also creates a generic function with one method, and this function is the same as the function above. It's a shorter syntax. You can also, of course, define functions with default argument. Here we're creating a new function that's called name, and it also takes one argument, but the difference here is that this argument has a default value. So actually, if I try to run add2 giving it no argument, I get an error message because add2 needs one argument, and because there is no default value, you have to provide that argument. If you don't provide it, of course, you get an error. When you have default values, you don't have to provide values for the argument. It will default to what you have there. So I'm creating this name function. And if I run it on the string Julia, I get my name is Julia. Because that function, what it does is that it prints my name is your argument. And you can see, by the way, how easy it is to play with strings. You have great string interpolation and string, like everything with string is extremely easy and convenient with Julia. But now, if I run this function without any argument, my name is unknown. We revert to the default value of the argument. Now let's have a quick little look at plots. There is one package that I think is extremely cool. It's called Unicode Plots. You have to install it. And I really like it because it allows to plot within the command line. So, of course, the plot is not what you would put in a publication, but because it runs in the command line, if you work remotely through SSH, for instance, that can be extremely convenient if you want to quickly plot something, to visualize something. That's great. You don't need a GUI. So I think that could be very handy for cluster work. But if we want something a little bit more, a little nicer looking, there are other packages, of course. The package, I'll be using several packages here, but the main package for plotting is called Plots. And Plots allow you to use different backends. So you could use GR, as I'm doing here, as a backend, but you could also use Plotly or several backends very easily. So here I'm using Plots with the GR backend, and I also loaded other packages for some of the plots I will show. So those plots are extremely basic, obviously, but just to give you a tiny little feel. So if I define two variables, x and y, one is 10 integers from 1 to 10, y is I'm generating y with the rand function, which is extremely convenient and flexible to provide all sorts of random numbers. And my first plot that I'm drawing with the plots package is over here. So it's the same histogram we've been plotting in the command line before, but in a nicer interface. So this is like the default thing. I haven't added access labels and titles and tweaked anything. This is just throw the code, and that's how it comes out. So by default, it already looks pretty decent, and of course, you can customize it greatly. Now, if I run a normal distribution, and that's why I loaded the distributions package, I get a normal distribution here. If I plot a little scatter plot, I get a little scatter plot. Not very pretty without tweaking, but that's totally fine. And then I can have two little plots. And then by running plot and as arguments the 4 plots I just created, I can easily put them all in one screen, one picture. And obviously, you can define if you want. Default is 2 by 2, as you can see, but you could put them vertically in a line, and of course, it's highly customizable. And if so, all the little bits of code I've been running are on the slides that I will post online. So if you want to play with it, feel free to do so. But I also added a link to the plots package website because it has lots of easy and very cool looking demos. So you could go have a look there. So that was a very, very brief, very shallow little intro to Julia for people who have really never used it. But in so little time, there's really little we can cover. But what I really wanted to talk about is parallel programming. So you can launch Julia on multiple threads. For those who use the Juno IDE, that will happen automatically. But if you launch Julia through any other way, Julia will be launched using one thread. But you can easily launch Julia on however many threads you want, if you have them, by setting the environment variable Julia num threads. So in a terminal, in a shell, not in Julia, you can run export Julia num thread equals however many you want. so just like any other environment variable. But you can also launch a Julia session, also again in your terminal, with that environment variable only for that one session. So, for instance, on my machine, I have 4 cores. So I launched Julia on the left panel just by itself. Now, on the right panel, I am launching Julia with this Julia num_thread equals 4 environment variable. So they look the same, but the command to see how the number of threads that Julia has access to within the current session is threads.endthreads. If I run this function on the left panel, I get 1. So Julia by default was launched on 1 thread, and on the right side, I get 4. So that's a very easy, convenient way to launch Julia on several threads. But that doesn't mean that Julia will run any faster, because making the threads available for Julia is clearly a necessary step to getting any parallel programming going, but it's not a sufficient condition. You also need parallel code. So let's run a very simple little loop. So what does this loop do? So for I in 1 to 10, print this little string, iteration I. So I is what will be iterated 10 times, run on thread, and then threads.threadID is a function that, it's a Julia function that gives you the ID of the current thread. So I'm also iterating over this so that I will have the thread ID, the ID of the thread on which each of these iterations was run. So if I run it, since I have only 1 thread, unsurprisingly, you can see that iteration 1, 2, 3, etc. were all run on thread 1. Now, if I pass the same function on my Julia session that has access to 4 threads, well, ta-dam, I get the exact same thing. So having made 4 threads available to Julia didn't change Julia's behavior. It didn't improve anything. It's as the language is in its current state, for loops aren't automatically parallelized if more than 1 thread is available. That said, there are extremely easy ways to do that. You have to transform your non-parallel code into parallel code, and the way to do this, or one way to do this, is to simply add this. So this @ is a macro. Julia allows to use lots of macros are a form of meta-programming, so it's a way there. You can think of them as similar-ish to functions. It's a way to add a level of programming on top of your starting code. So this threads.addThreads is a little macro that will allow to run our for loop in a parallel fashion. So let's use this code now. So not exactly exciting, because of course you won't be surprised to see that if I have only 1 thread available, parallel code is not gonna magically do something different, right? But now if I run this parallel code in a session where there are more than 1 thread available, then parallelism is happening. And because I am running Julia on 4 cores, you can see that 4 different calls were used. Iteration 1 was run on thread 1, 2, 3 also, but iteration 4 was run on thread 2, etc. So you can see that all those threads were used. But how does this affect timing? The previous loop is so fast that, of course, you can't get any information on timing with that. So let's make a very, very similar loop, but something that will take a little longer. So this time we'll have 10 million iterations of a very little computation, I to the power of itself. Here you will notice this little at time, so that's another macro. It's a macro that allows to time whatever function or like unit of code is right after itself. So this will allow me to time this for loop. So let's run this. So this was run in 0.67 seconds. And if I run it on 4 threads, 0.67 seconds, also because as we learned, parallelization of loops doesn't happen automatically. You need to add the macro that makes your code parallel. So now let's run a parallel version of this for loop, still with the little time macro to see how long it takes. So again, if I run it on the on 1 thread, if anything, it added a little time, of course, because the parallel code cannot be benefited from because we only have 1 thread, and there is a little extra time because the adding a macro adds yet a little something that Julia has to do. Now, if I run it on 4 threads, I see I have some speed up. It's not mind-blowing, but it did take advantage of the parallel code to get some speed up. And this is a pretty short computation. If you have some much longer computations, the benefit can be, of course, much greater. Also, I've been running these only once, and as you remember, Julia has just-in-time compilation. So the very first time you run something, things have to be compiled. So if we rerun these, now that they have been run first time, we might hope for some improved timing a little bit. Well, not a lot, actually, not much. So we did get a little benefit. But let's move on to the cluster to see if we can get more benefits having more threads, because I only have 4 threads available on my machine. So if you want to use Julia on the cluster, you need to load, of course, the Julia module. And if you run module avail Julia, module avail is a common practice to see the available modules. It will not show up because since Julia depends on the GCC module, it is not available right away, so you won't see it. The way to see it is to run model spider. So let's go onto a cluster and try all this. So I'm using Cedar. So I'm currently on Cedar. Sorry. If I run model spider Julia, I can see the various Julia versions that are available. I will use the latest, which is Julia 1.3. And because I mentioned Julia is a very fast evolving language, it's still under development. It really matters which version you use. For instance, the parallelization of the for loop I'm playing with was implemented quite a while ago, about 2 years ago. But now you can run parallel code on pretty much anything, and that's new to version 1.3. So it's very important to use up-to-date versions if you want to play with some of these features. So if I run module spider Julia 1.3, that will tell me how I can run the module spider. And as you can see, you need a GCC module, you need a compiler in order to have the Julia module loaded. So you have to load modules in order, since the Julia one depends onto the GCC one. But if you do this, now you have access to Julia. If I type Julia, I have access to Julia inside the cluster. Okay, so we need to create a job script to submit to Slurm. So first, we don't want to launch our job from our home directory. We'll go into Scratch. I created a little directory in Scratch that I called Julia job. So we'll run from here. So in this directory, I actually already created a job script that's here, job Julia loops sh. So let's have a look at what's in there. So, well, maybe this is a nicer format. So you need a bash shebang, then you need a number of sbatch information for Slurm. So it's optional, but you can give a name to your script. Here I called it Julia loop. Sometime here I'm only asking for 30 seconds because, as you saw, our code runs extremely fast. But of course, most of the time you would ask for much more than that. I'm just gonna ask for all the CPUs that are available on Cedar. That's 32. That's probably absolutely overkill for this, and a lower number might be more reasonable. But I'm just gonna try with that. Memory, I put 100 megabytes here, but actually I just played with things a little bit just before the webinar, and that's slow, that takes long, so bumping it up to 1,000 actually speeds things up. So in the actual script, we'll have something greater than this. Then you can have only one output file name for both the output and the error, but you can split them in two different files. So here I'm going to have Julia loop that %j will get expanded into the job number. .out, that's the data, that's what we care about, and then one file for any potential errors. So now, what are we actually running in that script? We will be running echo, running non-parallel loop on. This is the number of cores, so that's going to be 32 cores. So this is just going to print running non-parallel loops on 32 cores. Here I am running the same thing that I've been running here. Julia num threads equals the number of threads I want, Julia. I could add a script here, because you can run a Julia script from the command line by using the Julia utility and the name of that script. So that's what I'm doing here. I'm using Julia num threads equals, so this Julia variable that determines the number of threads. Here I'm using, again, the Slurm variable that determines the number of cores, so it's going to be 32 here. Then Julia, and then a little script. And below, the same thing, but with different script. Okay, so what are those scripts like? So they're in here. I already wrote them. So there is loop.jl. JL is the Julia extension for any Julia scripts. Of course, they're text files. It's just a convention to call them .jl. And ploop is my parallel loop. So that's the parallelized version of the code. So if I look at, oops, no, sorry, wrong word, loop.jl, I have my non-parallel for loop with the time macro to time it. So that's exactly the same code we've been running. And if I look at the C loop, it's the parallel version of that loop because I have this threads dot threads macro. Okay, let me double check. Okay, so we're running a little short on time. On my current script, I actually have 10. I'm asking for 10 cores instead of 32 because I was doing some tests just before the webinar. But that's totally fine. Let's run it with that. So the way to submit a job to Slurm is to run sbatch and then the Slurm script. So in our case, sbatch. Sorry, I'm in the wrong window. Sbatch job Julia loop. So the job was submitted to Slurm. Now, to check the status of your job, you can type SQ, which is a little Compute Canada shorthand for SQ, .u, and then your username. And oh, it already went. Since I'm only asking for 30 seconds, I guess that was easy. So that was, the job was 37, 54, etc. So let's see. Here I have, so 37, yeah, okay. So the two files for this run are the last ones here. You can see that the error file is empty, so that's good news. We didn't get an error. Let's see what we got in our output. So let's get Julia loop. So let me copy that. Okay. So running non-parallel loop on 10 calls, I got 0.8 seconds, and on 10 calls, I got 0.1 seconds. So when I did it, I lost it. But when I did it on my machine on 4 calls, I had a 60% improvement. Here you can see that we got an even better improvement. And earlier on, I tried it on 32 cores, and I had a 90% improvement. So it's not, it can probably be optimized to get much better than this, but clearly our code, our loop has run in parallel, and we clearly see an increase in speed. So that's, yeah, that's what I had on 32 cores earlier. So, I had a 90% increase from 0.8 seconds to 0.09 seconds. So this, of course, is all run on a single node with shared memory. So that's why I'm not using srun in my script. This is very basic parallel programming, but that's a little, a very small introduction of how things can be parallelized in Julia, including on the cluster. So if you have any questions, I would like to be happy to try to answer them.
So there were quite a few questions in the chat while you were talking, 5 or 6 questions, and I think Mason actually answered all of them. So I can certainly repeat them. So
great,
so there's a question whether Julia runs faster than NumPy in Python or not. So how does it compare in terms of speed to NumPy?
Well, it's supposed to be faster, but I don't know what Mason answered.
He said yes, it is.
Yeah. Supposed to be. So again, it depends. If you write really bad code that's not optimized, like very. There are ways that code can be extremely slow if it's poorly written, but well-written Julia code should be much faster than NumPy, even if you use NumPy, etc. Yeah.
So another question was how you can compile Julia code into a standalone executable. Then you can just copy, I guess, to a different machine or so. And
you don't have to. You don't have to compile it. You can directly run your script if you run, and that's what we're doing actually on Slurm.
But the question, yes, but the question is if you don't want to do that, you just want to have an executable. So, and the answer is yes, you have to use package compiler.
To make an executable. Oh, okay, okay. I don't even know that actually. So I'm glad Mason is backing me up because I'm still learning Julia. So there are a lot of things that I don't know yet. So thanks, Mason, for the.
So yeah, Dmitry noticed that when you were running the big loop with 10 million terms, you were doing I to the power I for I 10 million. You didn't get an overflow.
Oh.
Right? Because 10 million to the power 10 million is going to be a very large number.
I know, and I purposefully chose something very big because I was hoping to make something that would slow things down.
And the answer is you didn't get an overflow because usual types are not checked for overflow. So Julia will just ignore it. So you'll need to use special types to check for overflow.
Okay, so yeah, I should come with a computation that doesn't lead to something insanely large. Yeah, good point.
So in this case, it's actually good because not checking for overflow means that your timing was not affected. And so the last question is, so Mason just posted the answer, how does it compare to C in terms of speed?
Well, it is slower than
C. This is different.
Yeah.
Yeah.
So I don't know what Mason answered, but it's...
no, I think there was a different answer.
Yeah, because I mean, it's gonna be, if it's well written, it's gonna be faster than anything you could achieve in Python or MATLAB or R or any of the other ones. Even Python is getting a lot faster with NumPy and etc. But it still is far behind in terms of speed. But if you the fastest code is gonna be in C or C++. So if you know C and if you don't mind pre-compilation, that's still clearly the most efficient method. But if you want to have a single language that allows you to have an interactive session within a REPL, which is very nice for scientific development and testing things and processing and on-the-fly testing, like it has many advantages, and still have a very decent speed, that's Julia is a great option for that.
And then there's a question from Sajid. That is the last question in the chat. You can read it.
Okay. So could you shed some light upon how Julia interacts with C++? Okay. So Julia interacts very, very well and very, very easily with other languages. There are libraries that allow you to run Python code, R code, C code. Like the integration with other languages is extremely easy, and so it is highly compatible. Yes, so that part is great actually. So with Fortran, I don't know actually. I haven't looked at that. So with Fortran, that part I'm not certain. I'd have to double check that. But with C, R, Python, etc., yes, absolutely, no problem there. Okay, Mason says that with Fortran, the interoperability is also very good. So great, perfect, cool. Yeah, thanks very much, Mason, for your expertise there. And yeah, so since we have maybe a few more minutes, I'd be curious to hear more from Mason about the optional type declaration, because apparently I was wrong in understanding that declaring the type was a way to optimize code. So if Mason could go over this a little bit, I think that would be useful for me and maybe for everybody. If you don't mind, Mason.
Yeah, sure. So I guess the thing with optional types in Julia is that Julia will just go ahead and specialize all code to any types as soon as it receives those types. And that's independent of whether or not you put type type annotations in your function signature. And so the only thing that those type annotations are going to do for you are you can use them for multiple dispatch, in that you can use it for specifying different methods for different input types, and you can also do it to just restrict what sort of types go into a function. But from a performance point of view, it's identical. unless
okay, because I read some threads online that were saying otherwise, but that could have been absolutely wrong, and because
yeah,
I haven't.
There's
Sorry,
a lot of confusion about this because other JIT compilers are very different from Julia. Okay. So, for instance, Numba or PyPy, stuff like that, these all use a very different JIT infrastructure. Julia basically is like a ahead-of-time compiler, except it runs the the JIT compiler acts like a ahead-of-time compiler, but it runs right away instead of tracing and stuff like other compilers do.
Okay, because this idea I got it from a blog I read that was going over this, but I guess the either user was referring to an earlier Julia version, and things have changed a lot since then. That's very possible because Julia has evolved a lot, or that person was wrong in what they wrote then, because of course I had understood the advantage of type declaration if you want to define multiple methods for the same function, but I also read that it was a way to optimize code by preventing unnecessary compilations, and apparently that part was wrong. And so thanks very much for clarifying, and I will look into that some more. So
there is a macro you can use for this called no specialize. If you put that in front of a function signature, then it will not compile new versions for different input types. But you have to opt into that.
Okay, I see. Okay, cool. All right. Yeah, I will look into. I will look at that. Okay, so before we close off, so there is a little web page for this webinar. So if you click on this picture, that will lead you to the slides that I've been presenting. The video, once it becomes available, will be added here. But at the bottom, there is a section for questions and comments, and all you need to be able to post there is a GitHub account. So please feel absolutely comfortable to put questions and comments in there. And so Mason, I will look for that post that I had read, and I will put it in the comments. And if you are interested and if you have time, and feel free to comment on it. I would be interested to have your thoughts on that post, if I find it back, but I think I'll be able to find it back. So, and the way to get to this page, so WestGrid has a training material part in its site, and if you go to programming, and then you go to the Julia section in the table of contents. So this is still pretty small because I'm just starting. Oops, what happened? I'm just starting to learn Julia, so there isn't all that much yet. But this link leads you to all the WestGrid Julia resources. So yesterday I gave a workshop on Julia that you can find in here. And that also leads to the webinar. So you can find all that from this. And so if you have questions or comments, if I made mistakes, don't hesitate to correct me. I'm learning. If you have questions, also post them on. I will do my best to try to answer.